All right, welcome everyone. Thank you for being here. My name is Blake Keeler, and I'll be talking to you today about the two-point Weyl law on manifolds without conjugate points. So just as a point of notation, I'm always going to be working on a compact manifold MG, which is smooth, without boundary, and of dimension little n, which is always at least 2. I'll also denote by delta G the positive Laplace-Beltrami operator, so there's an implicit negative sign in the definition of the Laplacian that just makes my life a little bit easier. And because of the compactness of M, we get an orthonormal basis of eigenfunctions phi j with the property that the Laplacian applied to phi j gives back lambda j squared times phi j, and these are L2 normalized. And here I will list the frequencies lambda j in increasing order, repeated according to multiplicity, and they tend to infinity. Now, there are many different physical interpretations of eigenfunctions. Among them are that they encode the heat and wave propagation on your manifold, so they play the sort of role of sines and cosines in your typical Fourier series analysis. But perhaps more interesting than that is that if you take the phi j and you take the modulus squared times the Riemannian volume form, this gives you the probability density of a quantum particle with energy lambda j squared. So there are some very deep connections with this, between quantum physics and the study of eigenfunctions. So the main question for this talk is, how do the frequencies lambda j and the corresponding eigenfunctions phi j behave as j tends to infinity? So we would refer to this as the high frequency limit. Or if you prefer to rescale things, it's the same as the semi-classical limit as h tends to 0. So to study this question, I'll introduce two primary objects of interest. The first being the eigenvalue counting function n of lambda, which is just defined as the number of indices j so that lambda j is bounded above by lambda. So it's the number of frequencies that are less than lambda. And more generally than this, we have what's called the spectral function, denoted by pi lambda, evaluated at 2 points x and y in my manifold. And this is defined as the sum over all frequencies less than or equal to lambda. And I take the pointwise products of eigenfunctions phi j at x times phi j at y. So this is the Schwartz kernel of the spectral projection onto the eigenspaces with eigenvalue less than lambda squared. And to see that this object is more general than the counting function, namely that it contains strictly more information, we can evaluate the trace of pi lambda, which is the integral of the restriction to the diagonal, and we get a sum of a bunch of ones because of the orthonormality property, and this exactly returns to us n of lambda. And as a point of vocabulary, the asymptotics of n of lambda and pi lambda as lambda tends to infinity are generally referred to as Weyl laws. Now, Weyl laws have a long and rich history, dating all the way back to the early 1900s with the work of Weyl for bounded domains in Euclidean space. But the first main result I want to talk about is for the case of compact manifolds without boundary, which is due to Abakumovich, building on earlier partial results of Levitin in the 50s, which states that for any manifold MG, the counting function n of lambda looks like a leading term, which is lambda to the dimension, times this constant that depends on m, plus a remainder, which is like lambda to the n minus 1. So it's one polynomial power better in lambda as lambda tends to infinity. And we also have the following on-diagonal estimate for the spectral function. So if you fix an x in m, then pi lambda evaluated at xx looks like, again, lambda to the n, where now the coefficient is a smooth function of x, plus a remainder that is, again, like lambda to the n minus 1. And both of these remainder bounds are sharp, and this can be seen on the round sphere, where the symmetry leads to large multiplicities of your eigenvalues, which in turn gives you the maximal remainder growth. Now, this was generalized later on in the 60s by Hormander. In fact, it's more general than what I've stated here, but I'm interested primarily in the case of the Laplacian. Hormander showed that for any MG, there exists an epsilon positive, so that if the distance between x and y is bounded by epsilon, then pi lambda at xy looks like, again, this lambda to the n minus 1 with a more complicated leading coefficient. And it's maybe a little bit suspicious that there's a dependence on lambda here, but this leading coefficient is explicit, and I'll write it down in a second, and that will assuage your fears that this may interfere with the growth in lambda. And here our remainder function, r of lambda xy, can be bounded as follows. We can take the supremum over this compact neighborhood of the diagonal of the remainder function, and this is bounded by, as you may have guessed, lambda to the n minus 1. Now, I've intentionally left these awkward spaces here because this was later added on to by Xu in 2004, who showed that you can use similar techniques to show that if you differentiate the remainder function with respect to the spatial variables x and y, this leads to an estimate which increases the power of growth in lambda by the order of differentiation. So here alpha and beta are multi-indices, and these absolute values denote the length of those multi-indices. And as I mentioned, this leading term, this leading coefficient is explicitly computable. You can write it down as an integral over the unit ball in the cotangent fiber at x of this oscillatory factor against the canonical volume form on the cotangent fiber. And we see that the dependence on lambda is actually quite mild. It's a smooth bounded function of lambda, and so it doesn't interfere with the lambda to the n growth. And also when we differentiate with respect to x and y, we will pull out additional powers of lambda so that even though the remainder increases its growth by powers of lambda when we differentiate, the leading coefficient also increases its powers by the same amount, and so it remains the leading order term under differentiation. And these estimates are once again sharp by just considering the case of the round sphere. So what I'm interested in is improvements in the remainder for the Weyl law, but that's going to require some geometric assumptions. At the very least, we need to rule out the case of the sphere. And it turns out that the correct geometric quantity to make assumptions about is the geodesic flow. So there's an intimate connection between the asymptotics of pi lambda and the structure of the geodesic flow on M, and that can be seen in a fairly straightforward way. So if I write down the definition of my spectral function pi lambda, and I somewhat trivially rewrite this sum as a sum over all j from 0 to infinity, where I've inserted this characteristic function of the interval minus lambda to lambda, evaluated at lambda j. So I haven't really done anything here except add a bunch of zeros. And then I'll replace this characteristic function by the inverse Fourier transform of its Fourier transform, which leaves me with the following expression. So I'll end up with a sine t lambda over t times this infinite sum of cosines evaluated at t times the frequency lambda j, and then these pointwise products of eigenfunctions. Now I've skipped over a detail or two, and I've interchanged a sum and an integral, but it's not too hard to justify that this is actually a valid operation, at least at the level of operator kernels. And we recognize this infinite sum as the spectral representation of the cosine propagator, this cosine t square root Laplacian. So I can write my pi lambda in terms of the inverse Fourier sine transform of the function 1 over t times cosine t root Laplacian. And just as a note, this cosine t root Laplacian is the solution operator for the wave equation with vanishing initial velocity. Now we make note of the following general fact, that the Fourier transform intertwines growth and decay at infinity with singularities and smoothness. So if something is very smooth on one side, you take the Fourier transform, that will yield something that is very nicely decaying at infinity. And similarly, if you have something which is singular, and you take its Fourier transform, that will lead to some degree of growth at infinity that corresponds in some way to how bad the singularity was. And we also know that the singularities of this cosine propagator will move along geodesic spheres. This is a manifestation of the finite propagation speed for the wave equation. And so as a result of this, it's not unreasonable to expect that the growth of pi lambda, as lambda tends to infinity, should somehow be related to the geodesic flow on M. And indeed, this is the case. This is not just a heuristic. And this is well illustrated by the theorem of Duistermaat and Guillemin from 1975, which showed that if the set of periodic geodesics has measure 0 in S star M, so in particular that means Liouville measure 0, then the counting function n of lambda satisfies an improved Weyl law. So n of lambda looks like the same leading term that's never going to change, plus now a remainder which is like little o of lambda to the n minus 1. So it's ever so slightly better than the general result. And this was later improved by Safarov in 88, and then later independently by Sogin-Zeldich in 2002, who showed that under the assumption that the set of geodesic loops starting at x0 in M has measure 0 in the corresponding cosphere fiber. So that's admittedly a slightly stronger assumption than assuming that the set of periodic geodesics has measure 0. But under this assumption about the geodesic loops, the spectral function restricted to the diagonal, so at x0, x0, looks like the leading term that we expect, plus again a little o of lambda to the n minus 1 remainder. So it's again slightly better than the general case. And this was improved fairly recently by Consani and Hanin, who showed that if the set of geodesic loops at x0 has measure 0, so same assumption, but now we have to pick a little r lambda, so a radius which goes to 0 as lambda tends to infinity. Then for any x and y in the ball centered at x0 of that radius, we have that pi lambda at xy looks like the expected Weyl law, but where the remainder now satisfies a better estimate. So here, if we take the supremum over this ball of radius r lambda around x0, the derivatives of the remainder function are bounded by little o of the same polynomial power as we saw before. So a tiny little improvement over the sharp result. So this maybe illustrates how difficult the study of Weyl remainders can be. We have these several results over the course of many decades just trying to eke out the tiniest little improvement over the general case. Now, my main interest is in quantitative improvements in these Weyl remainders. So I want an explicit function that tells me how much better the remainder is than the general case. So this is going to require some stronger assumptions about the geodesic flow. And one of the major results I'd like to talk about in this direction is due to Berard in 77, who showed that if MG has non-positive curvature, so this sort of implies that the geodesics all tend to spread apart from each other, at least linearly, if they emanate from the same point. Then in this case, the Weyl law for the counting function has a remainder which can be improved by a factor of 1 over log lambda. So we're back to a big O here, but we have a quantitative improvement in the rate as lambda tends to infinity. So this is significantly better than the little o results, but it's under a stronger assumption on the manifold. And using the same techniques in Berard's paper with essentially no modification, his results show that the same estimate holds for the on-diagonal spectral function. So pi lambda at xx has an improved remainder with an extra factor of 1 over log lambda. In fact, Berard showed this in the special case of n equals 2 under the weaker assumption that the manifold just has no conjugate points, which is not nearly as strong as non-positive curvature, but is slightly harder to work with. And there are certain technical geometric assumptions that Berard was not able to obtain in dimensions higher than 2. But this was later remedied by Fontenot in 2017, who showed that these logarithmic improvements of Berard still hold for dimensions higher than 2 with manifolds without conjugate points. And he did this exactly by obtaining those geometric estimates that Berard needed. Now I'd like to move on to the first main new result of this talk, which you may be able to guess at what it is because I've left a line suspiciously blank on this slide. Namely, I haven't shown you an off-diagonal version of the Weyl law for manifolds without conjugate points. And so that's the content of the first main theorem. So if we suppose that MG has no conjugate points and we fix an epsilon between 0 and half the injectivity radius, then as long as the distance between x and y is less than epsilon, my spectral function pi lambda at xy satisfies the expected Weyl law, but where the remainder function r of lambda xy satisfies an improved bound. So we can take the supremum here over this compact neighborhood of the diagonal. We can differentiate in x and y as many times as we like, and we end up with the expected power of growth on the remainder, but with an improvement of 1 over log lambda as lambda tends to infinity. So this is the fully general version of the Weyl law for the off-diagonal spectral function. And a natural follow-up question to ask when you see this result is, can anything interesting happen kind of far away from the diagonal? Is all of the leading order stuff really close to the diagonal, or can you get lambda to the n type behavior farther away? And the answer is no, and that's the content of the next theorem. So again, in the context of manifolds without conjugate points, and here we fix any epsilon positive, then for any alpha beta, we can bound the derivatives in x and y of the spectral function pi lambda itself. So we're not estimating the remainder here, we're estimating pi lambda, and we're taking the supremum over x and y, which are at least epsilon apart, so we're avoiding a compact neighborhood of the diagonal. And here the spectral function satisfies the same estimate that the remainder did in theorem 1. So this tells us that all of the leading order behavior is happening very close to the diagonal. And the only result in the literature that I'm familiar with that's similar to this is a theorem of Safarov, who showed that if you have a compact set K in M cross M, which avoids a compact neighborhood of the diagonal and satisfies some technical dynamical assumptions, then if you take the supremum of pi lambda over this set K, that will be at most little o of lambda to the n minus 1. So moving on to the third main result, I'd like to introduce a little bit more notation. So I will define a spectral cluster with this notation pi with a subscript of an interval lambda to lambda plus 1. And it's defined in the way you might expect. It's the sum over frequencies lambda j in this band, in this interval, of these pointwise products of eigenfunctions. So this is the orthogonal projection onto this band of eigenspaces. And for these spectral clusters, we also have a Weyl law type result. So for manifolds without conjugate points, as always, I fix an epsilon as before, less than half the injectivity radius. Then for x and y, less than epsilon apart, my spectral cluster satisfies an asymptotic, where the leading term is now like lambda to the n minus 1 instead of lambda to the n, and this integral is taken over the unit sphere in the cotangent fiber instead of the unit ball. And the remainder function satisfies the exact same type of bound as it did in theorem 1. So it's bounded by this lambda to the n minus 1 plus the orders of differentiation divided by an extra factor of log. And it is actually because of this extra factor of log that it is even meaningful to say that this is the leading order term. In the generic case, when your remainder is just like lambda to the n minus 1, the leading term that I've written down here is also lambda to the n minus 1. And so unless you have an improvement in the Weyl law, there is no way to really compare those two. And so you can't meaningfully state that you have a leading term for the behavior of these spectral clusters. And this result for spectral clusters has some very interesting applications in the study of monochromatic random waves, which is the last thing that I'd like to talk about for today. But just before I move on, as a small note, this leading order term can be easily obtained as the derivative of the leading order term from the Weyl law for the full spectral function. So moving on to the last topic, which is monochromatic random waves, which are an application of these Weyl laws. Monochromatic random wave, I'll define as a Gaussian random field of the following form. I'll denote it by psi lambda of x. It's a sum over frequencies in this band from lambda to lambda plus 1. And I'm taking linear combinations of eigenfunctions with frequencies in that band. And then I rescale by this lambda to the 1 minus n over 2, which roughly corresponds to dividing by the square root of the number of frequencies in this band. So it gives us a notion of averaging these eigenfunctions. And the kicker here is that the AJ are not deterministic coefficients, but instead are independent, identically distributed Gaussian random variables with mean 0 and variance 1. So we should think of this psi lambda as an approximate randomized eigenfunction. Now, these random waves were first introduced in the case of Riemannian manifolds by Steve Zeldich, who was motivated by Berry's conjecture. Now, I don't want to talk much about Berry's conjecture because it's somewhat vague and heuristic, but roughly speaking, it says that if your manifold has chaotic geodesic flow, then your high frequency eigenfunctions should, at least at the wavelength scale, behave like certain Gaussian random fields in Euclidean space with frequency 1. So there's a kind of universal scaling behavior that is conjectured for eigenfunctions on manifolds with chaotic dynamics. Now, a very interesting and important fact about these random waves is that their statistics are completely determined by their covariance kernel, or two-point correlation function, which computes the correlation between psi lambda at x and psi lambda at y. And this can be computed explicitly as lambda to the 1 minus n times this summation of Vj at x times Vj at y over frequencies in this band, which we immediately recognize as lambda to the n minus 1, or excuse me, 1 minus n, times the spectral cluster that I defined previously. So we immediately get some results about the covariance kernels of random waves from theorem 3. So that is the last result that I'll talk about today. So on a manifold without conjugate points, if I fix an x naught in M, and I choose now a radius little r lambda, which is allowed to grow like root lambda over log lambda, then in geodesic normal coordinates centered at this point x naught, we have that the covariance kernel at x naught plus u over lambda and x naught plus v over lambda. So here u and v are my geodesic normal coordinates that I've rescaled by wavelength. This covariance kernel equals some limiting function which doesn't depend on lambda, which I'll denote by pi infinity. I'll write this down in a second. Plus a remainder, which we can bound as follows. We can take the supremum over u and v in this ball of radius r lambda, and we take any number of derivatives in u and v of the remainder function, and these will all tend to 0 like 1 over log lambda. So this is in fact a convergence result for the covariance kernels of random waves. We're saying that in the C infinity topology, the rescaled covariance kernel will converge to this pi infinity function at a rate of 1 over log lambda. And this pi infinity is nothing terribly complicated. It's just the inverse Fourier transform of the spherical measure, which is in fact the covariance kernel of a Euclidean random wave of frequency 1. So these random waves have the kind of universal scaling behavior that is conjectured of true eigenfunctions in Berry's conjecture. But I, of course, have made no claims about how these random waves compare to honest eigenfunctions. So this is by no means a proof of Berry's conjecture or anything of the sort. And this corollary has also already seen some use in some recent work by Dierks, Nodin, Piccati, and Rossi, where they studied the distribution of nodal lengths for random waves on surfaces without conjugate points, and they derive a central limit theorem for these nodal lengths. And with that, I will stop. Thank you for your attention, and I hope you enjoyed. And I'll stop here on some references in case you'd like to do some additional reading.